so this work was I did this work when I was a PhD student, and with colleagues from your lab, with Torsten and Alexandru, and I mean the work focuses on how we can use performance modeling for in a way. I mean, what can we I mean, which insights can we get about performance using performance modeling, and how we can use it for a better kind of to achieve better scalability. So, so I guess this is a slide about the trends in the microprocessor world is not new. I guess you must have seen it lots of times before, but I show it here as a something which kind of was a motivation for this work, kind of an increasing number of like processes and just an increased parallelism. So I kind of this work was started. I started it in 2013 through 2015, and also there were some addition in 2017. So the cycle of performance engineering in HPC is basically, I mean, where we start was we start with what was kind of like some code, and we instrument it and do some measurements, which I call it observation. And then once we're done with that, we analyze what we have, what hotspots we have, and identify candidates for optimization. And then once and we perhaps optimize some parts, we repeat this cycle. And performance modeling comes in this analysis part as a way to understand how, like more like deeper behavior of the code. I mean, we can try analytically model some parts of our code, or empirically. And empirically, I mean, we just produce more models from the measurements that we have. And what specifically we look at in this work is scaling models that basically provide us with some insight or some idea of how the code behaves at higher scale. So sometimes when we just run the code on a smaller scale, we don't see. I mean, some problems or obstacles are not, they do not, we don't see them unless we. I mean, the model allows us to kind of look at a higher scale, and in my particular focus was kind of based on. I mean, you using an earlier work in our group, work by Alexandru Kalatoiu, and that kind of this initial work on performance modeling proposed this approach to for producing performance models from um, measurements on a smaller scale, and then by identifying a group of potential performance models that kind of have the same form, which is called performance model normal form, which is in this performance is basically combinations of polynomial and logarithmic terms, and from that kind of from this sort of group of potential functions and some specific parameters, like a search space was generated and fitted to these small scale measurements, and from that empirical models were produced. So that was sort of like an initial work on empirical modeling, and I used and then basically what I did in the work on validating the performance expectations, what was built on this work and propose this idea of just using that kind of empirical modeling to kind of validate systematically our expectations of performance. Kind of you can think about it as if we added this approach to the testing phase and in a software development cycle, where we can. I mean, in this way, if we get scaling models for our regions of interest in our code, or if we focus on high performance HPC libraries, where we can, whenever we update, whenever we modify these libraries or add new functionality, we can run. I mean, where we can produce new empirical models and compare what was what we had been before in kind of as in a way, so something like which is similar to this kind of continuous integration where we run unit tests whenever we update our code. And specifically, I mean, we proposed this scalability validation framework, which consists of 4 steps. The first steps, in the first step, we identify what's our code of interest, our functions, what we want to, what metrics we want to measure, and our performance expectations. I mean, like, for example, the code should behave like as a of log p. And then the second step is sort of we either we use an existing profiler, or we could create some little lightweight benchmarking tool, or lightweight benchmarking code. And this is, you can think about it as if we kind of creating or writing a small unit test. And the third step is like we're running, and I mean, kind of you using modeling tool to generate the scaling models and compare them to our expectation. So I mean, in terms of use cases, so in this way we can, if we have some, for example, if we don't have some initial expectation, we can have or just have some like initial model as a baseline, and then do like regression tests based on that model. Or if we have different versions of some library, we can compare alternatives by using kind of this framework on these two the different versions of the code. And to basically be able to say whether we have a match or approximate match, we used kind of simple rule that given the expectation, we define like limits for approximate match and kind of the limits when there's no match. Just using like halving the exponent of the leading order the term of the expectation. The same idea kind of just from these boundaries from like giving the expectation like and then just kind of taking the boundaries and recursive averaging the exponents. In this way, we populate the kind of the search space for our potential models, the candidates for the models, and so that's I mean that's that was sort of an initial idea, which later was to transfer them in a more like a more I mean like I mean it was later a master's thesis by one of our students in our group. And then the idea was to generate the search space automatically. I mean, in a more user friendly way. So the first use case for this kind of for this approach was like applying it on MPI collective operations and like MPI communicator related functions. So I mean, if we think about it, like the framework. The framework it has kind of four steps, and then the first step identifying the functions and the metric. The metric in this case is runtime of the function or the memory consumption, and the function themselves are the barrier broadcast reduce. I mean the most frequently used blocking collectives. and then once this first step, I mean, once we did this first step of identifying the functions, and the second step is running the benchmark for this particular case. I developed a very lightweight benchmarking routines, and the kind of the approach for the empirical modeling, which I used, and I mean, it's so specifically, I mean, this this earlier work on empirical modeling was implemented in a tool called excerpt, and I so it requires to produce the model. It requires for some of at least 5 data points, like at least so for 5 different values for the number of processes. Kind of we need to have the time measurements for at least for 5 or the data points, and once we have that, we can continue to the third step of the framework, which is generating the model, and then the fourth step, kind of validating the model against the expectation. So the initial test systems for this for this specific use case were, I mean, 2 systems in Jülich Research Center in Germany, and the third one was the system in the Swiss supercomputing center. All these systems are kind of retired now, or just upgraded to something kind of to the next generation. So it's I mean, the spoke work was carried out in 2013, 2014, but yeah, I mean, the result basically is like this kind of the table on this slide, where we have the expectations for the MPI for functions, for the MPI collective operations, and the communicator functions, where we have that from just from the literature or the MP ICH code, and then we get the models from the modeling tool, and we can see whether it's I mean, and we kind of in the fourth step we set yeah, kind of we assign the score, whether it's a match or it's a approximate match. One thing I wanted to mention here is that in the first step of the framework, we also identify so-called cross-function relations. It means that for if we look at an MPI collective operations, a cross-function relation would be that MPI all reduce should be I mean should be better performing than MPI reduce followed by MPI broadcast. In this particular example, that there was some. I mean, the model that we got for all reduce on bits, the length was I mean it was even worse than the combination of the models for for reduce and broadcast, and it's like a more serious case of like a mismatch in the expectation. So another thing I want to highlight is that on European machine we got the model that we got for MPI memory was basically verified by the fact that I mean it just the documentation that basically specified that the way parastation was set up is that it was using like a linear amount of like the amount of memory for each MPI connection was linear in P, and then when we're running the all-to-all benchmark, it just basically it exploded and then just the model kind of it was it's just a good example of how like through the model kind of we saw that it doesn't scale. I mean the MPI memory usage. So kind of the reasons for the discrepancies what we saw were potential reasons are is that the expectations provided by the user these expectations might be they might be based on either simplified network models, or there could be kind of a noisy neighborhood, meaning other processes could be communicating in the like in the same perhaps in the same kind of in the same I mean there might be kind of there might be sharing some communication connections, and if there's like another other application that could have a pretty intense communication that might influence another third possible reason for the discrepancy is that on some machines the collective operations are more optimized because there's a special hardware that optimizes these um, these functions. In a later work by one of the students, we also ran this use case on specifically on one machine, but with two different MPIs on that machine. And that machine is the Lichtenberg cluster in Technical University of Darmstadt, and there's I mean we checked the Intel MPI and yeah, in Intel MPI and OpenMPI, and also there were some so some matches and for one interesting thing to note is that the last column is a broadcast which we call litmus test, because we implemented that version of broadcast by ourselves, and then this kind of one of the I mean this is one of the features of the validation framework, that the some that we can have like another not just one version of the code, but our manually implemented version of the code, or a different version of the code, and if we know I mean if we manually implement that, we can have more perhaps more confidence in the expectation, and here we implemented this broadcast using the binomial tree, and then we kind of saw that the fact that there's a mismatch in the Intel MPI in that function, but probably points to the implementation, to some implementation problem. So the next big use case was parallel sorting algorithms. The problem is that we have a distributed sequence of numbers, and our output is distributed sorted sequence across all the processes, and we looked at three variants of algorithms, so-called splitter based, where it works by basically selecting splitters, sorting locally, and then just redistributing the data according to the splitters, and then merging these local sorted pieces of the data. And then also there's an option for parallel radix sort, which is like a normal radix sort, but runs in parallel, and mini sort, which is a very kind of special case when just one element per process, and all the implementations we kind of used in this use case were all based on MPI. So and it was run on, we ran it on Lichtenberg cluster and Uqueen, and the, there's yeah, and then also I mean it was so interesting, interesting things about for example, so some of these algorithms that they rely more heavily on collective operations. Like for example, Minisort uses MPI collectives pretty extensively, so that potentially might be the like the reason for a mismatch for so yeah, I mean it's it was yeah, it was an interesting use case. I mean, was and it was a number of algorithms, and then one other interesting use case, which was he was looking at just to trying this approach was exponential terms and not just not just polynomial and logarithmic terms, and and another work which looked at using this approach in OpenMP construct, which was performed on. I mean, the work was led by a colleague in a different group and in Darmstadt. So to conclude, the work basically proposes a kind of a way to do software engineering for extreme scale systems, but perhaps not entirely software engineering, but kind of continuous integration for extreme scale systems. And there is I mean the framework is based on 4 steps that the user kind of performs. So the first step, the first 2 steps are manual. I mean, the first one is just identifying the code the code of interest. I mean, the metrics, the functions. The second step is just performing the benchmarking, and that step could be either if we write the benchmark ourselves, it's a manual step, or we can use an existing profile, and then an existing profiler such as Scalability. And I mean the modeling tool excerpt is able to use outputs from Scorpy, and so it's and then the third and the fourth steps are automated. So the whole framework has basically this tool chain that could be used, and we examine. I mean, we looked at a number of case studies. Well, one again, MPI collective operations for parallel sorting algorithms, and one potential direction which I could consider was actually use it, maybe adapting that to a production environment here in Livermore. By I mean the idea is to try to integrate this kind of modeling and benchmarking into Livermore performance tools. As there's the Hatchet tool, which just looks at performance profiles, and then Spot is like this web-based tool to see performance trends over time. So I mean, the idea is somehow kind of to do the modeling in Hatchet and present the results in Spot. So this kind of will take. I mean, the idea is to take this into a more production environment. So it's right now it's just an idea, but it might turn out to be kind of an interesting an interesting direction to turn this work into like see it at work in a production environment. So that concludes my talk.